Okay, so we're continuing our study of the Schwarzschild metric, and now it's time to look at spaceships that are in orbits around the Schwarzschild metric and better understand curved space-time. Well, we don't have to start this from scratch. We wrote down what serves as a one-dimensional equation of motion for it last time. I'm reinstating the angular momentum L, so I have the fully general situation here. It's one-dimensional. I'm looking because of the symmetries of the problem. Okay, I know that the orbit occurs in a plane. Okay, and I can get rid of my phi variable in favor of angular momentum. Okay, because it's conserved, because of the symmetries of the problem, and I can write down the equation of motion for the particle, because I know also that the total energy is conserved over here, right? And so I have dr by d tau, and then I have some spatial dependence like that. Now, okay, so it's the same strategy that I used when I solved the Kepler problem in Newtonian mechanics. I reduce it to a variable to a one-dimensional dynamics problem, okay, where my dimension is my radial coordinate, and for Newton, my time is my universal time. Here, I get it as an equation in a radial coordinate, okay, and a time coordinate, which is the proper time. Okay. And it's fully relativistic and all of that. I write it in standard form, okay, so 1/2 mv squared, okay, where the mass, of course, of the spaceship cancels out of everything here, because I'm doing gravity, and I haven't even mentioned it. I don't need to mention it, okay, and so I have this term. I put on all of my R dependence, that's V effective, and that's equal to the conserved energy squared. So I'm just writing down the relativistic analog in Newton's world of potential energy plus kinetic energy is total energy, and that's conserved. Okay, now okay, but I've redone all of those concepts in this framework, and I know how to proceed. Okay. And so now I just form the effective. I have to take, I multiply everything out. I have a constant, that's not too interesting to me. I have a minus my gravitational potential, okay? Then I have an L squared over R squared. I recognize that, that's my centrifugal barrier. If a particle has an angular momentum, okay, and the angular momentum is conserved, that angular momentum represents a centrifugal barrier. It makes effectively, from the perspective of a one-dimensional equation of motion, it makes the origin repulsive by a factor of 1 upon R squared. And then I get a big surprise. Oh my God, I get a term which is more singular than the centrifugal barrier. It goes like 1 upon R cubed, and it's proportional to the angular momentum squared. And we're going to have to think about that. That's the first deviation from Newtonian mechanics that gives rise to some of the famous effects of relativity. So we're studying the orbits of a planet, like around the sun, and if I set up that problem, I write this down, okay? My mass would be the mass of the sun, etc., okay? Okay, and I see a term, a correction, it's relativistic, goes like 1 upon c squared relative to the static Newtonian potential. And it says, in fact, that the origin is unexpectedly attractive, especially to particles with angular momentum. Okay, so we're going to have to understand that. It makes the system look very dangerously unstable. Okay, an attraction that's very singular. We'll have to understand that. So I compare that to the radial equation in Newton's description of the Kepler problem. Okay, so in that case, I know that my effective potential for the radial coordinate is the naive potential, and then corrected by the repulsive centrifugal barrier. Okay, and we remember in many cases how important that centrifugal barrier is. If you've done some elementary quantum mechanics, you know that centrifugal barrier, of course, pushes the orbitals out from the center of the atom, which might be a proton or a nucleus, and they control, and the centrifugal barrier controls the shape of the wave functions, okay, the spherical harmonics, for example, and it controls the spectroscopy of the system, okay, and the repulsiveness of the origin provides a stability for the quantum system. We don't have that here, and we'll have to get used to that. We'll have to see how that works, and we're going to study it. Okay, so the striking difference here occurs that for L different from 0, B effective diverges as minus 1 upon R cubed when R goes to 0. So this will make it impossible to have stable circular orbits for small r, as distinct from the Newtonian physics, where I can get stable orbits for any r. That's not going to be possible in general relativity because there's just too much attraction in the system. If you're looking for stable orbits, of course, then you'll plot this potential as a function of r, and you'll look for minima and stable minima. So the minima will be the points where dv by dr is equal to 0, and they're stable as long as the second derivative with respect to r of v is positive. Okay, the usual ideas, and that's written down here, right? This stability result is very important. It means that if I have a particle in orbit around a mass point, if I perturb it slightly, then the potential goes up, and so the particle can oscillate around that minimum, but it doesn't fly off. If the sign is wrong and this is down, okay, then I'm in an unstable maximum, okay, and a slight deviation, a slight push on that particle throws it to very different radius, and that's not a stable condition. That wouldn't be of interest. Okay, so let's look at the condition that has to be satisfied for me to get a minimum of B effective and then make a stable minimum. So the condition that I have a minimum, I just have to take this fellow, differentiate with respect to r, and set that to 0. So I'm just looking for the minimum, and I see that gives me a criteria here. It's a function of r and L. L is conserved, and so L squared. I do my arithmetic for the numerator here, has to satisfy this equation. Okay. So the first thing I see, that's a sensible equation, but not if r is less than 3gm over c squared. So if r is less than 1.5 times the Schwarzschild radius, this condition is impossible. Okay. So first of all, I learned that I'm not going to have stable orbits. Okay, stable circular. I'm not going to have any orbits at all. Okay, if I'm inside 3/2 of the Schwarzschild radius. Okay, there can be more restrictions as well, because that's only my first condition, but that's certainly the case. Okay. Okay. Now, in addition, of course, if I'm looking just for circular orbits, then the rate of change of r with respect to tau has to be 0 at the circular orbit. Okay, if that's the case, then I know that E squared is equal to twice B effective at that r, and I can put that in and then replace E squared by a function just of r. Okay, and so I do that. So now I'm specializing down to circular orbits. Okay, and so that's the case. Okay, I also had the situation that I have an orbit that V effective was at a minimum or a maximum. Okay, that L squared was equal to this, so I can combine these formulas in particular, and I can, for example, solve r as a function of L squared. Okay, in fact that only involves this equation. I'm just taking this equation and I'm solving for r. Okay, as a function of L, and I read off from this equation again another constraint, that this equation only has sensible solutions if the stuff inside the square root is a quadratic equation. You see, just take it and square it up, and it's a quadratic equation in r as a function of L squared. And I see I'm not going to have a meaningful solution, a real solution for any set of parameters. I see that L to the 4th can't be too big. In fact, there's L fourth here and L squared here, so L squared can't be too big. It has to be less than 12 g squared m squared over 4 squared. Okay, otherwise there's no circular orbits. Finally, in addition, I have to look for stable ones, okay, and I check that the second derivative of the effective is positive for r plus in this, and that the other case, r minus, they're unstable. Okay, so I learned from this that L squared has to be greater than 12 g squared m squared over 4 for stable orbits to exist. And if that's the case, then plugging into this formula, I see that r plus has to be greater than 6 gm over c squared. So I can have stable orbits around my planet only for distances greater than 3 times the Schwarzschild radius. Okay. So I can do my ordinary dynamics, my ordinary particle dynamics easily enough in this framework, and that's what I learned. Okay. Okay. Now let's make a comment about the additional term that played such an important role in all of this algebra. All of these constrictions and such come from that new term, which was an attractive term that was proportional to L squared over R cubed. Okay, this is the term that causes the precession of Mercury, right? This is the new term that general relativity gives to the Kepler problem. For Newton, the Kepler problem was solved by ellipses, right? You've done that in mechanics, and you remember that it was the 1 upon r potential was very special. It gave rise to ellipses that were stable in space-time. Okay, that is, you have a sun here, and the Earth goes around it, and the Earth goes around it on an ellipse, and the ellipse just continues around every time, retracing its step. Okay, and that's a property of 1 upon r potential. That's discussed in one of the supplementary lectures that I do on Newtonian mechanics. Okay, to show that that's a special effect. Closed orbits occur only for special potentials. 1 upon r is a special potential, and the harmonic oscillator is another one. But for other potentials you might think of, the orbits won't be like that. They'll spin around. They'll precess. Okay, and so this is a special effect. But now we have a small additional term, small in the application to Mercury, a small additional term, okay, which you treat as a perturbation on the Newtonian solution. And the dominant thing it does is it takes the ellipse of Newton and it precesses it ever so slightly. Each time it goes around, the Earth precesses slightly. Well, it's a very small effect. You see, it goes like 1 upon c squared, okay, etc. Okay, so it's very small compared to the other terms in the equation. So how can you see it? Well, you can see it because it accumulates. Every time the Earth goes around, it'll precess a little bit. But after many, many centuries, of course, it can be an appreciable effect. And in the case of Mercury, it becomes an appreciable effect. And there are the small effect that general relativity predicts fits the experiment. Now the experiment's very complicated because I illustrate the concepts by reducing everything to a two-body problem. But the solar system is not a two-body problem. There's all those other planets around, and all those other planets are going to cause perturbations in each one's orbits, and so there's a large amount of precession in Mercury's orbit due to the other planets. Okay. So Venus, Earth, all of them perturbing the orbit of Mercury. Mercury, of course, is an inner planet, and so the 1 upon r term, 1 upon r cubed term, is more effective for it than for planets that are very far away, like Jupiter. So you can find it in Mercury, but now with modern, very accurate technologies, we see these effects everywhere. Okay, so you have to solve the Kepler problem for the multi-body problem, and you do that with perturbation theory. And at the end of the day, there's a discrepancy, 43 seconds of arc per century. I think it was a problem since you know, Kepler's problem is studied for hundreds and hundreds of years. It was a residual problem in the business, in physics and astronomy for I think 200 years, and then general relativity came along and solved it. Okay, so which led to people taking general relativity very, very seriously in the early days, although it was based on ideas that were very unfamiliar. Another thing that pushed people toward general relativity, of course, was the bending of light as it goes around the sun. Okay, there was the famous excursion of Eddington to measure the bending of light around the sun in an eclipse. Okay, in 1919, I believe. The predictions of Newton and general relativity differ by a factor of 2. The factor of 2 coming from the curvature of space. Okay, and Eddington's result favored general relativity. That made the headlines, made everybody famous, and there you go. Okay, and that's fine. It turned out that really some of those measurements were very challenging, and to really make a decisive case with good statistics for lensing of light around the sun, you have to do a very thorough analysis, and it backs up that analysis backs up the early measurements, which might have been subject to considerable controversy. But what about this extra term? Okay, well, let's take the extra term. Here it is, gml squared over c squared r cubed, and understand it. Well, I see embedded in it is the good old gravitational potential. Okay, and what's left behind is L squared over R squared divided by C squared. Well, okay, well, that's angular momentum. Okay, so that goes like V squared times R squared. It's angular momentum per mass. So this term is just a velocity squared over C squared. Okay, so this is the extra energy due to the angular motion of the particle. So I have a problem. I'm trying to reduce it to 1 dimensions. Okay, and then I have my angular motion, which contributes to the effective potential. In the case of Newton, I know what it is. It's L squared over R squared, the centrifugal barrier. In the case of Einstein, there's that term. In addition, there's this term. There's extra energy in the one-dimensional problem due to the fact that the particle is actually executing motion in 3 dimensions. That extra energy, of course, is good old energy, and it's attracted to the origin. Okay, so the extra term is just a manifestation of universality. It's a nonlinear effect that has to be in gravity, because gravity says all energies of whatever form attract. And so that's the idea of it, you see. And I needed the 1 upon r squared here, okay, to get at an equivalent mass. This has the dimensions of basically of a mass. If I restore all the masses to my equations, okay. So it's a energy over c squared, a mass that comes from extra kinetic motion, and it's attracted to the origin because everything's attracted to the origin by the rule of the equivalence principle. Okay, and that's what it says, and that's the reason for it. It's a manifestation of the nonlinearity of general relativity, and we'll find other manifestations of the nonlinearities as we go. It's interesting, however, to return to the problem of the infalling particle again. Okay, and write down the lifetime for particles with L different from 0. Remember, we did the problem of the captain falling into the black hole, but he was falling in along a radius. Now, if he's falling in with angular momentum, his lifetime is now changed by the appearance of this extra term downstairs. Now let's take a look at this extra term. We see that if R is less than Rs, then the extra term in the denominator decreases the proper time for our poor captain, okay? Because there's a minus sign here, there's a minus sign here. This factor becomes negative inside the Schwarzschild radius. This is negative, so L squared contributes, it's positive, and it decreases your lifetime. So this is what I was saying before. you're inside the Schwarzschild radius, you're trying to escape. If you have a rocket ship, you turn on your motors as quickly as possible. But that dooms you to die earlier, because you see you're trying to fight geometry. Geometry says that your future light cone aims toward r equals 0. Your future is at the singularity, not at time equals infinity, because the light cones have switched over. So you more quickly go to the singularity, and you have a lesser lifetime, and it shows up here in this effect. So it's interesting, and we can understand it. Okay, so there's more discussion of this variety in the supplementary lecture, and take a look at it, because now we're going to move on to other sorts of problems. I want to look at the geodesic deviation. I want to look at the stresses in space-time, okay, that have to do with curvature, and so we'll pick that up.